Hello all and welcome to our webinar Where the Measurement Counts. We're going to be talking about Endress+Hauser as a skid solution provider and also the Prosonic Flow G. But just before we get into the essential information today, I'm going to be going through the GoToWebinar interface. So you can see on the screen here that you can increase or decrease your webcam window there, as you can see in the diagram. And throughout the webinar, we've left about 10 to 15 minutes at the end to answer any questions that you might have. So feel free to type these in the question box on the right-hand side throughout the webinar when you think of them, and we'll address them at the end. We're not going to be doing the webcam part of it this time, and also there'll be a survey at the end of the webinar where you'll be able to give us your feedback and also ask us for further information or any other questions that we missed out on during the webinar due to time constraints. So I'm just going to briefly introduce myself. My name is Taylor McCurdich. I'm the industry manager for mining and oil and gas, and I've been with Endress+Hauser for about 3 years now in the marketing team based here in Sydney. I'm now going to hand over to our other two presenters, Jason and Ryan. So we'll start off with Jason.
Yes, my name is Jason Metcalf. I'm product manager for the ultrasonic flow meters. I'm located in Rhinoch, Switzerland at our headquarters. I've been with Endress+Hauser for over 20 years. Been in the product manager for flow for 20 years at the headquarters here. Previously, I was working at Endress+Hauser United States, so quite a long list of experiences here in flow. And now I'll hand it over to Ryan.
Yeah, thank you, Jason. Good afternoon, everyone. My name is Ryan Wilson. I head up the project department for Endress+Hauser in Australia, predominantly looking after the execution and delivery of customer projects on time, within budget and specification. And yeah, I've been with the company for 11 years. I come from the oil and gas industry, so yeah, bringing with some of the knowledge that I've gained through my experience in the oil and gas industry. Thank you.
Excellent, thanks Ryan. So what I'll do now is briefly go through the agenda that the webinar will be for today. So Jason's going to kick off with the Prosonic Flow G 300-500, their benefits, and also some applications that we can apply this device to. Then he'll hand over to Ryan and he will talk about coal seam gas skid, and then Endress+Hauser as your local skid solution partners, so where the measurement counts. And finally, to wrap up, we'll be hosting a question and answer session. So now I'm going to hand over to Jason.
Okay, thank you, Taylor. Okay, so I'm going to start off right here. We have our ultrasonic inline portfolio. We actually have 3 meters serving inline measurement for ultrasonic. On the left is our original entry into inline measurement. That is our Prosonic Flow 92F. That's a liquid inline meter measuring liquids only. Then to the right, we have our B200, Prosonic Flow B200. This was our first gas flow meter, inline ultrasonic, doing low pressure applications, really focused towards biogas applications. And then we have our new product, which is the main reason I'm here to talk about today. This is the Prosonic Flow G 300. This is the compact one. The remote version is the 500 version. So okay. 1 second. Okay, there. Okay, so before I get really started into the features of the product itself, I just want to go basically through the measuring principle. A quick little overview of that. On the top right, you'll see in the picture there is a cutaway of a pipe. We have an arrow indicating flow from left to right, and on this pipe we have some transducers. These transducers are going to create and receive ultrasonic pulses. You see that they're set at an angle. When a pulse is sent with the flow, it has a certain time to cross. We measure that, and then we actually do that do this in the reverse direction, so it's going against the flow, and we measure that time. What happens is the ultrasonic signal is actually accelerated in with the flow and decelerated against the flow. So we get a time difference, and that time difference is proportional to the flow rate in the pipe. Obviously, we just see one set of transducers here. You can have multiple transducers in the pipe, but for demonstration purposes, we only show one here. And that's the basic measuring principle. So sounds traveling faster with the flow and slower against the flow when we measure that time difference. And the reason this is important, so that is the basics on the flow. So it's very critical for good time measurement, generating nice clean signals, so you can do accurate measurement to calculate the flow rate. So the new product we have is the Prosonic Flow G 300/500. Just sales released this year, earlier this year. We have it in size ranges from 1 inch to 12 inch. So that's 8 different sizes in between there. And we have a pressure rating of class 150 or class 600. The measuring uncertainty is 0.5 with our premium calibration. That's a 5-point calibration, or with a standard 3-point calibration, it's 1%. Now that is non-corrected volume flow. If for corrected volume flow, where you're compensating for pressure and temperature, the uncertainty is 1% with our premium calibration and 1.5% with our standard calibration. The meter has worldwide approvals, so it can go into hazardous locations, obviously, and we also have some approvals on the strength of the meter body versus pressure. And we also have the SEAL approval, which is safety integrity level for safety critical loops. We have a mains power supply transmitter. It's on our new 300/500 platform. We just introduced this platform across all of our product lines, so we are also serving Coriolis magnetic flow meters, some other types of technology, and we're all moving to this new platform, and we're doing that. We have titanium transducers on the inside, so we have 2 different types of metal. We have the cast meter body itself, which is stainless steel, and then we have inside where the piezo's are actually located, that is a titanium design, because titanium gives us a good signal from the meter. And we specifically designed this meter for difficult applications, so where you have wet gas or having liquid carryover. A lot of times other flow meters fail in those type of applications because the condensate creates too much noise in the system. And we really have some special features in here to combat that problem. We also have integrated pressure and temperature. If you're looking at the picture on the left, the piece sticking out on the left side there, that is our pressure, and our temperature is located directly underneath the transmitter. And so we both have the pressure and temperature as an option. If you do get the pressure and temperature, we have what we call integrated gas analysis package. And this allows us 2 different features. One is compensating for pressure and temperature to get into standard cubic feet, so corrected volume. And the other one is like a concentration measurement of methane, and I'll get into that. And we have heartbeat technology, which is telling us the health of the device. So it's a diagnostics capability going into how healthy the meter is operating, seeing if there's anything wrong. Where we think we really separate ourselves out versus other manufacturers is on our ultrasonic transducer design. We've also, just like I said earlier, we've designed this meter specifically for wet gas conditions. Not every application is nice, clean, dry gas. Sometimes we get applications where we can have some difficulties with liquid carryover or condensate. We've specifically designed the meter for that. We have, as an option, integrated pressure and temperature. Like I said, the gas analysis package, and we calibrate every single one of our meters. This is not necessarily typical with other manufacturers, but for us, every single meter is flow calibrated. So it does go on a flow calibration rig. And we have our heartbeat technology monitoring the system and its health of the meter. So a little bit about how this is working, what we've done with the transducer design. So on the left, this is the transducer that sits inside the meter body. So this is internal. This is where we're creating the ultrasonic signal itself. And you can see down here on the bottom left, that is the yellow part is the piezos. That's what's going to generate the sound. And it's also receiver. So you have a set of transducers in there. One is transmitting and the other one is receiving. So you're sending that signal upstream and downstream, so they reverse. And so with the piezo, what we want to do is use all that energy and as efficiently as possible transfer it into the gas so we get a nice clean signal. We'll show here what we've done in the animation. If you look now to the center, we're going to start this animation. The piezos are going to start vibrating. Obviously, this is amplified, so you can get the visual on here. And in the center, it's hollowed out. And what happens is the energy is going to be condensed and then really exerted all at one time. So we amplify the signal to get a nice, clean, sharp signal. So here we go, we see the vibration, the piezos, that energy from the ultrasonic signals being concentrated as it goes around this hollow piece in the middle, and then you get one big kind of like a trampoline effect of transmitting that sound into the gas. And you can see on the right side, we got a picture of a graphic on the signal waveform, and what we're really looking for is what we have here, which is a nice, clean, quick signal. So you want to get it out quickly. What you don't want are what we see here, which you can see the bottom left that was just popped up in the graphic. We have a lot of noise. So you have a lot of noise in the background. It's hard to tell the true signal versus the noise. The other one is you really don't get a strong peak. And when you're doing this time differential, it's hard to find exactly what measurement value we want to take from that type of elongated signal. So that's on our transmission. As you know, when we transmit, the other transducer is looking to receive. And what we don't want is that these piezos are generating sound, is that the noise from the piezo goes out one direction into the gas, but it's also going back into the transducer and into the meter body. And this can run around the pipe inside the metal and be transmitted to the other piezos, creating noise in the system. And so what we want to do is filter this out. So here what we've done, again, piezos are here. We're going to see this popping up in the animation in a second. And we have these masses that filter out the ultrasonic signal. So we start vibrating, and these mass blocks actually start to dampen out the ultrasonic signal, stopping that from traveling outward and creating noise within the system. And what happens also, we see here the piezos are vibrating, but if we're getting ultrasonic noise from other things like valves, those type of things, these mass blocks filters actually work in the opposite direction also to protect our piezos to have that they're only receiving the true flow signal values. As far as wet gas and some of our features that we put into the meter to overcome the difficulties in applications is, you'll see on the left side, this is one of the problems that happens. It is, we have this filters and we're trying to keep noise away from the system. If you have, on the left side, you can see that we've bridged a transducer with some liquid in there. What happens is you can filter as much as you want, but now the ultrasonic signal, if it's in the meter body, is short-circuited right directly into the transducers, and you don't want that. It's what we call bridging. So what we've done, if you look in the middle now, this is a cutaway of a meter. We have quite a large gap in between what I call the socket and the transducer. to avoid any type of bridging. Okay, so there we have a large transducer gap. What we've also done is where the socket meets the meter body, we've actually grinded out an angle to encourage the condensate to drop out. I'll show you in another picture. In addition, on the right side, we've had, if the meter is installed in a vertical installation, we've added a drainage hole. And here's what it looks like in reality. So on the left side, you can see where the arrows are pointing. This is, we've machined inside. So if you put the transmitter on top or on bottom, it works both ways. We've machined so you get condensate is encouraged to drop out of the socket there. And then we have the drainage holes. This was a cutaway demonstration model to give you a sense of how big the gap is. On the right side is the true transducer for that size meter. You can see it's quite a big gap in there. And then we have the drainage holes for the vertical installation for dropping the liquid out. Now, I mentioned earlier that we have integrated pressure and temperature directly into the meter. We do not use our IOs for this. So it's directly going to our amplifier, what we call an ISEM. And so it goes directly into that. So if you order it, the cabling, everything is done. It's directly integrated into our ISEM. So it's no wiring or anything that you would need to have to do. We also, I'll mention it a little bit later, we do a heartbeat check. So we're also checking the diagnostics of the pressure and the temperature. We get some different diagnostic codes and we're able to analyze that inside of our transmitter. If you order the pressure and temperature, we have a special software package. This allows you to do corrected volume flow, so standard cubic feet per minute or hour, and also a gas analysis as far as methane content or combustible content. And so we see here, this gas analysis package has 6 different modes. We can also do single gases, so that's easy. What we can do is do gas mixtures up to 8 different components. So when we do the corrected volume flow, we're doing all those compressibility factors for all those gases. It's also able to do this dynamically with our Modbus option. And we have what we call our coal seam gas biogas. We're quite experienced, especially in biogas and coal seam gas, with doing a gas analysis. So what we're doing is generally there's only 3 components coming up. You have your gas, water vapor, and CO2, traces of some other stuff. And what we do is we're monitoring how much methane. There's a big difference in sound velocity between methane and CO2. And so since we're measuring the time of flight from one transducer to the other, and we do that in the reverse direction, the average, we can actually, we put that, we do the average of upstream and downstream, you get the speed of sound in the gas stream itself, and we're able to determine how much methane is in there. So this can give you a good indication how well the well is working or producing at any one point. It's not a gas analyzer, it's more of an inline process measurement to allow monitoring. And then we have some different calculations for natural gas using different standards that exist in the market. And we have one that's our own, very similar to the coal seam gas, where we're using the speed of sound to determine how much combustible material is in the natural gas. This is the first flow meter on the market with SEAL. SEAL is for safety critical applications, stands for safety integrity level, and we have different ratings on there. We have SEAL 2 and 3. This is a standard called IEC 61508. And so right now we're the only one on the market with a SEAL approved device. Now, I mentioned earlier, we do flow calibrate every single meter in-house. We don't do this externally, we do it in-house, so this improves our delivery situations and also our cost position by calibrating in-house. Our calibration rig, We have several of them, but we had to build a new one for this particular device. It goes from 2 to 12 inch. For the smaller one, we calibrated on a different gas calibration rig that we have in-house. We can do a flow range from 2 meters cubed per hour up to 8,700. That more or less, the high end of the rig right now is 40 meters per second. We can go higher than that. We can go all the way up into about 60, 65 meters a second. The problem is the stability. So right now we specify at 40 meters per second. And most importantly, the measuring uncertainty of this gas calibration rig is 0.25%. And this is all traceable. We use a system of turbines and positive displacement rotary pistons to keep it to national standards. I mentioned quite a few times about heartbeat technology. One of the most important things about heartbeat is checking all the diagnostics, but what we have inside is our critical measurement value is coming from time, okay? And we use a quartz crystal for that. What we've done is integrated a second quartz into the transmitter. And what we use this second quartz is to see if there's any drift in the main reference quartz for the flow value. So we're able to see if the meter's being affected at all over time, if it's drifting or not, and we're doing checks on that. We're also doing the standard diagnostics checks and everything. Heartbeat then will be able, it can give you a report, so it's checking your cables, your internal resistances, those type of things. Afterwards, with the heartbeat, you get what we call a heartbeat verification report, telling you the health of your meter, if you're good or you're bad, or maybe you need to send it back for recalibration or such, or what the problem is. That report can also be used for your documentation trail on the device. So obviously the meter is new, but we had to do some testing beforehand. And what we did here is we're tested a meter, a DN300, so 12-inch meter at a place called Pascal Labs in Stuttgart, Germany on natural gas. Okay, we sent there. This was before we had our calibration rig that I showed you earlier. So this meter actually went out uncalibrated. So it was just by design, we measured all the tolerances. We take great care to make sure that each meter is very precisely made. This is especially true on the transducers. We measure each and every single one of them to make sure it maintains a certain tolerance. If there should be a failure on a transducer, you can put a replacement one in and it will be exact same dimensions. You do not need to recalibrate the meter. But continuing on about testing of the meter, we're going to test it at 3 different pressures, and the uncertainty of the rig at Pascal Labs is 0.25%. So these are the results. From left to right, we're starting off with 21 bar, higher pressure, and then we're well within our specification. 6 bar, as pressure decreases, this has always been a challenge for ultrasonic meters. So normally some of them would stop working at certain pressures. We are actually able with our meter to measure down even into vacuum conditions, slight vacuum conditions. And so you can see as we move left to right, we're decreasing the pressure, but we're still maintaining our accuracy with this meter. And just to repeat, this meter was not calibrated. So it was not flow calibrated, so there was no linearization done on it before it went out. So where do we see this meter going into? Some typical application could be a 3-phase separator, for example, on the gas leg. We have products that cover all 3 legs here, but we see that going on to separator applications. So we just get there. This was a field trial that we had in the UAE. This was for the replacement of turbine meters. They had difficulties with their turbine meters because of mechanical wear, and they wanted something with no moving parts that was more reliable in the application. And they also liked the fact that we had our integrated pressure and temperature here. And so this was actually going to be used for billing. We do not have custody transfer approvals on this meter, but when two parties agree they want to use it for billing, they go ahead. And so this one going into a natural gas application, like I said, eliminating any moving parts. So very maintenance free versus what had been previously in the application. We also tested this internally because in our factory, obviously we have a natural gas supply for our boilers and such. We've installed it there and we're actually using it for the efficiency of our building. So monitoring how that's working. It's into a complete energy monitoring system with some other components that we have within our portfolio at Endress+Hauser. In the main application, which I'll let Ryan go into the details that we're really targeted, especially in the Australian market, is coal seam gas here. And we see this mainly because a lot of the features we built in are able to handle some of the robust, or some of the difficulties in the gas leg of the coal seam gas, such as condensate buildup, water carryover, those type of things. And so really coal seam gas is another typical application that we are focusing on. Okay. And with that, I will hand it over to Ryan to go into a little bit more about our coal seam gas solutions.
Yeah, thank you, Jason. Yes, just to kick off, I think what we'll do is we'll just look at a little bit of the background of Endress+Hauser and how Endress+Hauser fits into flow metering skid solutions. Get to the next slide. There we go. All right, so just a little bit on the background. So Endress+Hauser is a well-known instrumentation company, but we also have in-house engineering capabilities, and we provide standalone skid solutions where the measurement counts. So what that means is that we build complete overall turnkey solutions where the measurement on the skid itself is the core function of the skid itself. And that's where our expertise lie. Expertise lie with the control and management of the process. Endress+Hauser has extensive experience in the CSG industry. We've been developing and building skids for some time now, and we have many skids in the field installed in Australia as well as in other countries where we've done a lot of R&D projects with our customers. We've established a reliable, tried and tested supply chain for the fabrication of skids. And the key point around that is that Endress+Hauser directly manage the compliance to Australian standards for the Australian market, but also the quality is also managed directly by Endress+Hauser. So though the skid fabrication work might take place in different countries and by third-party partners, the whole fabrication process and the delivery of the project is managed directly by Endress+Hauser. And just to add to this, this will lead into the Endress+Hauser skid design. Endress+Hauser has a global alliance with Rockwell. So this has allowed Endress+Hauser together with Rockwell to develop a complete turnkey solution, which also incorporates the control system. There are some key benefits with using the Endress+Hauser solution, and we'll just take a look at that now, together with the Rockwell integration. Endress+Hauser skids are also available as standalone units, so they don't have to be integrated with the Rockwell system. Like I mentioned, there are some key benefits to doing that way for the end user, but the skid is able to be integrated into alternative control systems if that's the requirement. We also provide a build and supply offering whereby the design is not from Endress+Hauser, it's from maybe an EPC or from the customer or end user themselves, and then Endress+Hauser will actually build and supply that skid, incorporating Endress+Hauser instrumentation. Yeah, So just a little bit of background on the Rockwell Endress+Hauser alliance. So as I mentioned, there's some key benefits by using the Endress+Hauser field instrumentation coupled with a Rockwell control system. So we have a complementary product offering, which allows us, as I already mentioned, to provide a complete turnkey solution. Both companies have invested in integration, development, and testing. So what that means is we have developed standardized faceplates and control blocks, which makes the integration of our field instrumentation, of the Endress+Hauser field instrumentation, with the Rockwell control systems very seamless, thereby saving an engineering effort. So we can reduce the time required from an engineering point of view to get the field instrumentation to work seamlessly with the control system, with the Rockwell control system. The Endress+Hauser experience from this is further enhanced with this tight integration, and it also provides more information. So more information becomes available, such as health data. We spoke about heartbeat technology, so we can bring that information back up into the control system, maintenance information, and running online verifications as well. Okay, so now we just dive in a little bit on the detail on the Endress+Hauser skid design, the Endress+Hauser offering for the CSG gas market. So just to start from the beginning, so the key outcomes that Endress+Hauser looked at when designing the CSG gas skid, the three main outcomes, I should say, was to measure the gas flow accurately, to measure the water flow accurately, and to provide a facility whereby we can separate the water and gas coming from the well. Now, of course, there's other functions on the skid, such as overpressure protection, and also the management of the flow using a control valve. But Endress+Hauser really focused on these three key outcomes that we think that every CSG gas skid should do, and it should do well. So just to say, so the Endress+Hauser skid is designed to measure and control CSG well water and methane gas while providing a separation facility, which is an inline facility. The gas and water flow outlet lines would continue on to a gathering network. Normally water would go to a reverse osmosis treatment plant, or alternatively a settling pond, and the gas would go for further separation and to a gas compression station. All right, so then we looked at the process diagram to understand the process, and this has come from a lot of work that Endress+Hauser has done on the CFD modeling side, but also some R&D projects that we've done with the customer in Botswana, and the knowledge we've gained by working with the CSG industry over many years. So just to explain the process at a very high level, so there's two process lines that come from the well. The one is the gas line and the one is the water line. I'll just start with the gas line. So from the gas line of the wellhead, we go into a control valve, which is primarily there to control the flow of the gas, but is a key component, as people in the CSG market understand, is a key component for starting up a well as well. It then goes through our key measurement point, which in this case on the Endress+Hauser skid design is the G300, which Jason has just presented. And there's some key benefits around using that flow meter in this particular application, but I'll go into more detail on some slides later on. Now we go down to the bottom, which is the water line. So the water line, also coming up from the well, goes into our gas vapor eliminator, which is our inline separator. That separator can then divert gas flow back to the gas line and can divert water down to the water line. And I'll go into a little bit more detail on how that all functions on the next slide. All right, so that's the 3D model of the Endress+Hauser skid design for the CSG gas market. And you'll see there that we purposely put the gas line at the highest possible point by still keeping in mind the need to keep a very low profile. So we understand that a lot of these skids are on private property, but we had to reach a balance between the process functionality and keeping a low profile. But the skid is relatively compact and has quite a small footprint in comparison to other skids that we've seen out in the fields. So the top line is as high as possible because we want to encourage as much separation as possible. Now, on any well-managed gas well, most of the separation should be taking place inside the well itself, so underground inside the well. However, that's never going to be 100%, and there's also process upsets that are experienced. So we want to, as far as possible in the design of the skid, design the skid to separate out as much of the gas from the water as possible. So that's the reason why we've got the gas line right at the top. You'll see there, as we saw on the PNID drawing, that the inlet coming from the well on the gas line goes into our control valve, which is primarily there to control the flow of gas, but more so to control the startup of the well. So we don't want to have the maximum flow rate right at the start of the well, because we need to manage the potential of collapsing wells, and we need to bring up the well in a controlled manner. It then moves on to go through our ultrasonic G300 flow meter, and Jason's touched on this a little bit in his presentation, but I'd like to just go into it in a little bit more detail in this particular application. So the G300 actually offers many benefits in this application. So in coal seam gas, in a lot of wells where there's a higher flow profile of the gas, there's a lot of solids carryover, and the solids carryover is primarily coal fines and sand in some cases, and of course that's very abrasive. And already I've mentioned that this normally happens when we get higher flow rates. So when the flow rate picks up, obviously the higher the velocity, the more abrasive it gets. So you've got an abrasive material coming through the flow meter, and you've also got a higher flow velocity, which is sort of a recipe for the perfect abrasive storm inside a flow meter. So the benefits that we have on the Prosonic G300 is that, first of all, the material of construction. So the transducers themselves are made out of titanium, which is obviously a good material for abrasive applications. But even through design, we've taken into account this abrasive situation that we need to manage inside the flow meter, and we've actually recessed the transducers. So that means that the transducer face is not sitting in the direct flow path of the methane gas and solids carryover coming through the flow meter. And this is a key factor, because if you've got a leading edge inside the flow path, even if you have titanium sensors, it's very much prone to abrasion. And that's the key point measurement or primary measurement on the flow meter, and if you have failure on the transducer, then you lose the measurement point. So we wanted to make sure that we manage that well. Another aspect of coal seam gas is it's a wet gas, and we very often get water carryover, even coming over up into the gas line. And this is predominantly happening when you have process step changes or process upsets. But the flow meter itself is very well designed to, first of all, handle wet gases, but also by design has drainage facilities inside the transducer sockets to avoid the bridging that Jason was talking about earlier, bridging between the transducer and the inside body of the flow meter itself. So there's some key points there. We also have the integral temperature and pressure measurement on the flow meter itself, meaning that we can do corrected volume on board the flow meter as opposed to doing it maybe inside an RTU on a control system. And it's there as an option if we want to do that. So that is key for us on our coal seam gas skid design, the G300 flow measurement point. And as one of the important outcomes that we wanted to achieve on our design was that we would have an accurate and reliable gas flow measurement. I'd like to just drop down to the bottom of the drawing now. So you'll see there that there's a 1-inch inlet line that goes into our inline separator. Just to point out that our inline separator design uses standard piping components, which means that it's not certified it's not regarded or categorized as a pressure vessel. So there's some key advantages there. If it's a pressure vessel in Australia or in Queensland, for example, it's got to be registered, and there's some ongoing operational costs in terms of inspections because it is a pressure vessel. So we've kept our design using standard piping components to design our inline separator. The other key point on the design of the Endress+Hauser inline separator is that we actually do level control inside the separator. Now this is key. We have seen a number of designs in the field where there is no level control inside this inline separator. We believe, or Endress+Hauser believes from our CFD modeling, that in order to achieve maximum separation inside the separator, you need to have control of the level itself. So what typically happens inside the separator is that well, you can see there's two level switches there, the Liquifence FTL50s. So there's a low level switch and a high level switch. And those level switches will be monitoring the water level inside the separator. And the primary role of those level switches is to switch isolation valves. So you'll see there's a 1-inch, on this particular diagram, it's a coaxial solenoid valve, but it's also available in a ball valve version as well. And you'll see there's one on the water outlet and there's one on the gas outlet. What the level switches will do will detect if there's water approaching the top of the separator, then it will shut off the valve going to the gas line, thereby ensuring that we don't get water carryover into the gas line. And the bottom solenoid valve will be the bottom Liquifence level switch will be looking for gas. If that sees gas, then it will shut the water outlet valve, thereby ensuring that we don't get gas down the gas water line. And then what happens in the gathering network downstream is it actually gets vented off to atmosphere and high point vents, which obviously we don't want. It's methane gas, so from an environmental perspective, it's we don't want to be venting methane gas to the atmosphere, but also we want maximum yield out of the well, so we don't want to waste gas. We want to collect and recover as much gas as possible, and that's the functionality of the separator in terms of the level control. The separator, of course, the primary function is to provide a settling time. We do have an option to increase the diameter of the separator. And also to provide a blowdown facility on the separator itself. And the blowdown is if we get too many solids carry over and we don't get good flow, then there may be a requirement to blow down solids from the separator from time to time. The water flow then goes through behind that upright on the structure of the supporting structure of the skid. Is a magnetic flow meter. So that's a tried and tested method for measuring water flow using magnetic flow meter from Endress+Hauser. And we have all the suitable liners and electrode materials to be able to accommodate the coal seam gas industry applications. It then goes through a non-return valve, and that's there just as a safety to ensure if we get any spikes in pressure downstream that we don't have backflow coming through the skid itself. Okay, so that's the skid, the demo. Well, that's the Endress+Hauser design. This is a demo skid. I call it a demo skid, but it's actually a fully functional skid. But its materials of manufacture are slightly different. It's stainless steel piping. The frame itself is powder coated, and that's not typically what we'd have on our standard production model, although it is available as an option. But typically on a standard production model, we would have a galvanized frame with our carbon steel piping. Yeah, this was a photo taken from a joint presentation that we did with our alliance partner Rockwell. You can see the Rockwell control panel on the left-hand side. This system is fully integrated using standard faceplates and control blocks. It's also got the heartbeat technology functionality programmed into the control system, so you can automatically run a heartbeat verification. So this is looking at the health of the instrumentation. On this skid, you can run a health or a verification of the G300 flow meter. You can also run a verification of in this case, we're using a P300, which is one of our magnetic flow meters. And you can run the heartbeat verification and check the health of the instrumentation itself. You'll see there that we use a FlowServe control valve. We've been working with FlowServe for many years now. And there's actually some subtle differences on this particular valve, particularly designed for the coal seam gas industry, and it's got to do very much with the coupling between the actuator and the valve stem itself. On the standard model, there's some play there within tolerance, but we didn't want any play in between the actuator and the shaft to ensure that we had very fine control. And this has to do with when we're starting up the well itself. In addition to that, there's been a number of firmware updates on that actuator to increase the accuracy of control on that flow meter. There is a ICX-D certified assembly. So all the equipment on the skid has ICX-D certification. The skid is inspected in accordance to AS 60079, so fully in compliance with hazardous area requirements of Australia. Once the skid is installed, there's a requirement for an HA audit in some states in Australia, and this is a service that we can assist with as well. All right, so I'm conscious of the time that we have, and we want to have some time at the end for questions. So I'll move through this quite quickly, but please feel free to type in any questions at the end if I've missed anything that you want to know about. So I've already mentioned, so small footprint. We understand that it's important that we keep the footprint or the profile of the skid as low as possible. Also, the design has taken into account the stacking of skids in containers, so this helps us in terms of the logistics of transporting the skids and keeping the costs down. No separator. When I say no separator, we have an inline separator. There's no standalone pressure vessel separator, and we do that on purpose, as I've explained earlier on, to avoid having the complexities around managing a pressure vessel and the ongoing compliance requirements on the OPEX side. The skid is rated from 0 to 4,000 million scuffs per day. We found through our experience in the field and also with some of our R&D projects that we've done with customers, that's well within the range of what you would typically see as gas flow rates. In fact, most skids or most wells that we've seen are operating more or less around the 1.2 to 1.8 million scuffs per day. The water flow rate is rated up to 18 meters cubed per hour. And again, from the experience that we have, that's more than enough to manage the dewatering stage on the skid, as well as the normal operational stage of the well itself. The nominal flow rate is 2 meters cubed per hour, but can, as I mentioned, go up to million scuffs per hour. But as I mentioned before, can go up to 4 million scuffs per hour. The gas flow is controlled by electrically operated flow serve valve. So this control valve, again, there to manage the startup of the well, but also to manage the flow rate during operation as well. A separator to catch gas carryover water line is level controlled. This is a key difference to what we've seen with other separators in the market, inline separators, and is a key requirement in terms of managing the separation of gas in the separator. Gas flow is measured by Endress+Hauser's new G300 ultrasonic gas flow meter. And another point I didn't mention earlier, but this flow meter has a very high turn down ratio, which is beneficial in the coal seam gas industry because the well typically has variable flow over its lifespan. So at the beginning, you normally see very high flow rates, it then drop down to some sort of stabilized flow, and then again would drop down to even another level when at the end of life. And if you're using alternative measurements, gas flow measurements such as orifice plates and DP pressure transmitters, then of course every time you have a substantial change in your gas flows, if you want accurate measurement, you need to go back out and change the orifice plate. And of course that's not, we can avoid that situation using the G300. The G300 as well as a full bore flow meter, so typically we see quite low pressures coming from the well, and using an orifice plate, for example, creates a huge pressure drop. So we're really starting with very low pressures, and to put an obstacle in the flow path that's going to create a massive pressure drop is normally not beneficial. So it's a full bore flow meter with very, very minimal or negligible pressure drop across the flow meter itself. Water flow is measured by the Endress+Hauser's P300 magnetic flow meter. On this case, we use the P300 because we have Ethernet IP functionality on it, but we can also have HART using our P200 magnetic flow meter. On the separator itself, we monitor the pressure using our Cerebar S, which is proven technology again and very reliable pressure measurement for this application. All right, just continuing on some of the features. So compact design with multiple connector. So as I mentioned before, this is a turnkey solution if it's purchased together with the Rockwell control system. And the way that we connect the skid to the control system is we use a multi-pin connector. And what we do is we take that multi-pin connector into the non-hazardous area. And what that does is allow us to control the cost. So if you're doing switching or connections inside a hazardous area, immediately the cost goes up. So we have an umbilical cord with a multi-pin connector. It's a plug and play. You plug it into the back of the Rockwell control system panel, and off you go. The system works. So it's fully FAT'd and functionality tested prior to delivery. So barring any damage during transport, it's a fully functional unit when it gets to site and plugged in and powered up. Power supply, so it's a 24-volt DC power supply to the system. It's using 237 watts. So in some remote applications, obviously power consumption is a concern, and we've kept the power consumption as low as we possibly could on the skid itself. Communication protocol, so on the standard Endress+Hauser offering, it's HART, but it's also, as I mentioned earlier, available in Ethernet IP, and there's some added advantages around using Ethernet IP in terms of the integration into the Rockwell system as well. Process information available on the standard offering is flow, pressure, temperature, and conductivity. This is coming, so flow and pressure can be measured directly on our flow meter on the gas line, but on the separator we have a standalone pressure transmitter. Temperature again is integrated into the G300, so we can get a temperature measurement from the G300, and the G300 is also able to measure conductivity. There are a number of other process variables that can be measured using the G300 and available as an option. As I mentioned, you can do corrected flow on the G300 as opposed to doing the correction inside an RTU or control system. There's an energy measurement, there's a methane fraction measurement, calorific value, and wobbly index. So there are a number of other process variables that are available as options and can be programmed, or the parameters can be set up so that that measurement can be taken from the G300 if it's a requirement for the application. Operational maintenance information, so I've already mentioned this, the heartbeat verification. This can provide local and remote diagnostics, so a very powerful tool for remote installations, which calcium gaskets are, and they're very dispersed as well. So there's many of them, they're in remote applications, and they're normally quite far from each other. So to be able to do remote diagnostics is a key functionality of the Endress+Hauser skid design. All right, and the standard material construction is carbon steel. I showed you a photo of one that we had at one of our joint events with Rockwell. That's got stainless steel piping. It's a demo unit, but the standard offering is in carbon steel, and the frame would be galvanized. However, alternative construction materials are available. Like I say, and with the piping as well, the standard offering also comes with a C5M coating system, so it's a marine grade or for corrosion environment as standard. The ENH offering is available in 150 pounds, 300 pounds, 600 pounds as standard, so there's no special there. That's a standard offering from Endress+Hauser. A lot of the skids that we see in the field have 150 pound or part 150 pound, part 300 or 600 pound. We can offer a complete solution in 150, 300 and 600 pound as a standard offering. Overpressure slam shut valves and overpressure relief valves are also available. Not all customers want to have that functionality on the flow metering skid itself, on the calcium gas metering skid, but they are available as an option to be incorporated in the standard Endress+Hauser skid design as well. And modifications to the separator system, and I mentioned this earlier, such as blowdown systems, larger separator section, etc., are available as an option as well. And really, what we like to do is, if a customers interested in the Endress+Hauser skid design, that we kicked that off with an engineering workshop where we worked through the actual requirements on site, and we're able to modify our standard offering to be able to, we believe, will fit 99.9% of the applications out there. We'll be able to fit with our standard offering, but of course, there's also options to have these modifications if there's a special condition that we need to take into consideration. Yeah, and just in closing, I just want to encourage everyone, in the handout section in this webinar, there's the Endress+Hauser skid design data sheet, and there's a lot more technical information in there. Of course, we don't have time today to go through all of that, but please feel free, if there's any questions, to contact Endress+Hauser. You can contact myself or Taylor, and we can provide additional information as required. Thank you. Okay, I'll hand it back to Taylor now.
Thanks very much, Ryan, and thanks, Jason, as well. So we've got a few questions coming in now. The first one will be for Jason. There's a question from Ravi. He asks, what is the special and the advantages of 4-wire transmitter? I thought this was typical.
Yeah, it is typical. The reason we have that in there is our previous designs, when I showed the previous 2 flow meters we had on the market, both of those were 2-wire devices. And so really for ultrasonic, most manufacturers are with a 4-wire device. Just pointing out that it is a little bit different if people were familiar with our previous product line, that this one is a mains power 4-wire device.
Excellent, thanks, Jason.
Yep.
I've got another question for you as well from Sanga. He asks, can this handle corrosive gas like power station flue gas, for example?
It really depends on what the composition is. We do have certain limitations as far as corrosivity. The 2 main components are as far as the metal is stainless steel and titanium, and most of them have quite good resistance. But you'd have to look into specifics to see if those materials are compatible. We also do have an O-ring in there that's a Viton type of material.
Thanks, Jason. Another question for you as well. This one's from Michael. He asks, can you please clarify why the difference in accuracy exists between uncorrected and uncorrected gas flow? Is this due to error stacking between the flow meter and the external pressure sensor?
The reason we have the 2 accuracy statements. One is volume flow and the other one is corrected volume flow. So the corrected volume flow, also you have an uncertainty on the pressure measurement and the temperature measurement. And so that additional uncertainty is accounted in by the uncertainty of the pressure transmitter and the temperature measurement.
All right, thank you. Another one for you, Jason. We've got a question asking price-wise and the advantages compared to a Coriolis flow meter in the same application.
Okay, so price-wise, as you get bigger in sizes, Coriolis meters get quite big, and there's a lot of material there. So at typically 1 to 2 inch, you're going to be saying that both of them are about in the same price range. But as you get bigger, 3 and bigger, really the price advantage goes to the ultrasonic meter. We actually have a lot less material of construction, so it's priced accordingly that way. You also, with the ultrasonic meter, you have no pressure drop. It's one of the disadvantages with the Coriolis, and also you need a certain amount of pressure. They can't go down to the low pressures that we have with the ultrasonic meter.
Thanks, Jason. I've got another question for you from Khaled. He asks, what are the upstream or downstream meter run requirements, if any?
Okay, it depends on what accuracy you want to obtain. So I always said we had 2 different accuracy statements. So for standard volume flow, not corrected, it was 0.5% and 1%. If you want to get to that 0.5%, you're going to need 20 pipe diameters. If you want 1% only, then it's 10 pipe diameters upstream.
All right, thanks. Another question for you, Jason. Can you please explain what is meant by this device being the only SIL certified device? Do you mean in terms of the ultrasonic flow meter devices on the market?
Yes, it's my understanding right now. There might be another one out there, but I haven't seen it yet. But we are the only one that has the SIL certificate on an ultrasonic gas meter.
Another question for you, Jason. You mentioned the wobble index. Can you please explain what this is?
Wobble index is an indicator of how much energy is in natural gas. So if you were to burn it, how much energy you could expect to get out of the gas being burned. So it's a quality measurement of the gas.
Excellent. Cool. Thank you, Jason. And we've got time for one more question. This one's for Ryan. Actually, a question about what is the estimate manufacturing time for one skid?
So normally we would encourage ordering skids in batches of 10. That's purely because 10 of the skid design, 10 units fit into a standard 40-foot shipping container. But typically for a single skid, you'd be looking at about a 4-month lead time. And that's got to do with lead times on some of the key components like the control valve.
All right, thanks, Ryan. Actually, we might squeeze in one more question for you as well. This one's from Anil. He asks, can we use this meter on vent lines to stack?
Is that for me or for Jason? Taylor?
Sorry, Jason.
Yeah.
I think you said something about vent lines.
Yeah, sorry. The question was, can you use this meter on vent lines to stack?
Yes, you should be able to do that. I need to see the specific details, but I don't see a reason why not right now.
All right. Okay, excellent. Thanks very much, Jason and Ryan, for your input today, and thank you for everyone for typing in their questions. Just quickly, once you've jumped out of the survey, out of the webinar, can you make sure that you complete our survey and let us know about your feedback that you have? And for those questions that we didn't get to answer today, we'll send you some further information about some of the questions that you've asked. So look out for that email. You'll also be getting a follow-up email from us, just giving you the presentation, the recording, and also some additional information around the Prosonic Flow G and the skid solutions as well. So again, thank you to Ryan and Jason, and we'll see you guys next time.